Here are the notes for day 106. This is the second day of Taylor approximations. First example says estimate the square root of 4.1 using a third degree polynomial approximation. This function and centered around c equals 3. If c is going to be 3, then the only way we're going to get 4.1 is letting x equal 3.1. And that makes sense because centering your approximation around 3 and substituting in 3.1, the value that you're estimating or substituting in is close to your centering value. Anyway, when you plug in 3.1, the square root of 3.1 plus 1 is 4.1, which we wanted to estimate. So if you start with your P3 polynomial format, we want f of 3 plus f prime of 3, x minus 3, f double prime of 3, x minus 3 squared over 2 factorial, and f triple prime of 3, x minus 3 cubed over 3 factorial. Your c value is 3, which is substituted everywhere you see a 3, and then in the end we're going to substitute 3.1 for x, but we're going to hold off for that for a minute. So here's my function, evaluated at 3, first derivative evaluated at 3, etc., etc. Substituting in all these values, we get this function here, and then when you plug in 3.1 for x, 3.1 minus 3 is always 0.1. So parentheses is 0.1, this parentheses is 0.1, this parentheses is 0.1. Picking up a calculator and cranking through all those calculations gives you 2.024845703. And then to calculate the error, I'm just going to plug the square root of 4.1 directly into my calculator. So the calculator gives me the square root of 4.1 is 2.024845673. The difference, the actual minus the estimated, is negative 2.999 times 10 to the negative 8, or negative 7 zeros and then a 3. So that's awfully accurate with just a third degree polynomial. So the next topic is figuring out what's called the Lagrange remainder, or the error. So an error is the same thing as the Lagrange remainder. And the formula is here, but we're actually going to use a slightly modified version of that, which appears down here. So just like alternating series, if I take this polynomial and extend it one more term, I get the nth plus 1 derivative, x minus c raised to the n plus 1, and n plus 1 factorial. But the slight difference is that for the nth plus 1 derivative, I want to maximize this value. So z is going to be some number between x and c that maximizes this quantity here. And there's also absolute values. We want just the magnitude of the error. So I need the absolute value of this and the absolute value of that. So for this third degree polynomial, I'm going to go to the fourth term, figure out the derivative, and then in order to maximize this quantity, I actually need to look at the fifth derivative. Since the derivative of this fourth derivative is positive, when I bring the negative 7/2 down, I get fifth. That tells me that the fourth derivative, since the fifth derivative is positive, that tells me the fourth derivative is increasing. But since the fourth derivative is negative everywhere, that means it's increasing but negative. So a sketch of the fourth derivative is right here. It's increasing because the fifth derivative is positive, but it's also negative. So the maximum of the absolute value of that, when I take this quantity here and take the absolute value, I now have a decreasing, and that tells me the maximum occurs when I plug in 3. So I'm going to use 3 as my z, and that's going to maximize this quantity here. So the rest of this is continued on the next slide. So there wasn't enough space on the next slide, so I went 2 slides further and finished up the remainder problem on this table of contents for the next section. But anyway, what's happening is now that I've figured out that the quantity is maximized when I plug in 3 into my fourth derivative, 3 plus 1 is 4, the absolute value of negative 15/16 4 raised to the negative 7/2. 4 raised to the negative 7/2 is square root of 4 is 2. 2 raised to the 7th is 128. And negative exponent means move it downstairs. So I've got 15/16 times 128. The negative disappears because I'm taking the absolute value. The difference between the 3.1 and the 3 is 0.1. Raised to the 4th is 0.0001. And then 4 factorial is 24. Simplifying all that using a calculator, I get 3.0517 times 10 to the negative 8th. So the remainder, or the maximum error for that third degree polynomial, is this quantity here. What I want you to notice is the 3 subscript means that the polynomial that we used to approximate was a third degree, but the remainder is actually based on the fourth degree term. 3 plus 1 is 4 up here. So the error should be less than 7 zeros and a 3, and the error we found on the previous screen was indeed less than that. So the last slide for this section, a little bit of review. Write the Maclaurin polynomial for y equals e to the x from memory. Okay, this is something you're going to get memorized eventually, but e to the x has a derivative that's always e to the x, so It's a very straightforward. And then now it says derive the Maclaurin polynomial for y equals e to the 2x. So you're going to go through the whole process of taking derivatives. Maclaurin means c equals 0. So when you take the derivatives and plug in 0, you get these coefficients, and then you build your polynomials. What I want you to notice is that this is the polynomial approximation for e to the 2x. If you compare e to the x and e to the 2x, I'm just replacing x with 2x. So can I do that with the original formula? If I take this x to the n over n factorial and change it into 2x to the n, you do get the same thing as if you went the long way. So once we have polynomial approximations for some transcendental functions, if you want to slightly modify them by changing what's near the x got changed into 2x, you can just jump straight to the original polynomial and replace your x with a 2x or whatever else is different. And then finally, another error example. Find the number of terms needed to estimate e to the 0.1 with an error of below 0.0001. So I'm going to start with my error formula. Okay, my remainder and my error means the same thing, and I need that to be less than 0.0001. So now do some work with this off to the side. Take your derivatives. E to the x has derivatives on and on of e to the x. So the nth plus 1 derivative is e to the x. E to the x is positive and increasing. Every derivative is positive and increasing. So if I'm going to substitute values anywhere from 0, which is my c, up to x, which is 0.1, anywhere from 0 to 1, you'll get a maximum output when you plug in 0.1, the right edge. So my z value is going to be 0.1. So between this x and the c, the number that produces the largest derivative value is z equals 0.1. So figured that out. Derivative with 0.1 substituted in, 0.1 to the n plus 1 over n plus 1 factorial. This time around, we don't know the number of terms. So these, n is the variable I'm solving for, and I want it to be less than 0.0001. So I'm going to bring e to the 0.1 to the other side, and now figure out this decimal 0.00009048. And what I need to do is just a little bit of trial and error. So when I plugged in 2, I got 0.0016 repeating. That is not below 0.409048. Plugged in 3, I get 0.000166, which is below. So that tells me my third degree polynomial will have an error less than 0.0001. So the third degree polynomial with 0.1 plugged in is 1.10516 repeating. When I do e to the 0.1 on the calculator, I get 1.1051 repeating. The difference between these two values is 0.0004, which is less than 0.000904. So there's a lot of very small numbers flying around, but this formula says that your error will be less than 0.0009, and the actual error we got was certainly much below that. Okay, that's it for the second day of Taylor's.